Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. We are in subsection 3.2.2. We're talking about binomial and multinomial coefficients, where they come from, what they are, and as a result of a counting problem. Let's start off with binary bit strings. We're going to be counting them of a certain length. So these are just strings of zeros and ones. So for instance, let's count how many binary bit strings of length 8 have exactly 3 ones. Notice how I've labeled these boxes 1 through 8 for the different positions, and think about what's happening with each of these. Here, it's kind of like having a position or that has, we're going to have a 0 or a 1 in here. Here we can have a 0 or 1. It's kind of like we're pulling either a 0 or a 1 from some place labeled as 8. So that's kind of like a committee, right? A committee that we're pulling things from. Sometimes it's kind of hard to know exactly how we should define our committees. But if we remember what the committees represent, they represent things that we can pull options from. We can pull things from. So here, notice we have 8 positions, and we can either have zeros or ones in each position. So it's kind of like each position is a committee, and you can get something from it. You can either get a 0 or a 1 from it. But you want, what do we want in the end? We want 3 of these things that we want 3 of the things that we pulled to be ones. So it's kind of like the sum of everything that we've pulled needs to be 3. So what we're pulling is kind of like we're pulling exponents. So we're pulling like a 0 exponent or a 1 exponent out from each committee, and each of those happen just one way, because there's only one way of getting a 0 from committee 8, and only one way of getting, so one way of getting a 0 and one way of getting a 1. So if we establish it in such a way, then each committee will look like this, like x to the 0, x to the 1, then one way for each, and so look like 1 plus x. Then we can multiply all these committee polynomials together. That's just 1 plus x to the 8. And remember that specifically, if we're looking at finding a committee of size 3, it's kind of like we're pulling different people from, so we can either pull 1 person or 0 people from each committee, and we want a committee of 3 people. So since we're doing that, we can work mod x to the 4th. So all our computations can be done mod x to the 4th, and since modding out by something like setting x to the 4th to be 0 in a merge that preserves multiplication and addition, merging or quotienting, modding out by something like this, by a polynomial, preserves multiplication and addition. So we can think about actually modding out before we get the final result, not just multiplying out and modding, but we can actually mod at each step. And that's due to multiplication being preserving. We can do it before or after, it doesn't matter. So we can kind of move the modding in at each and every step along the way, which is really nice. I mean, first of all, we could think of this as 1 plus x squared, and then multiply that 4 times to itself, so, or to the 4th power. And we could further rewrite it like this: 2 times 2 times 2 is 8. Let's see. Yeah, except for this guy right here is actually 1 plus x squared. So we multiply 1 plus x squared out, and then we raise that to the 4th power, and I guess we've divided that into a 2 and a 2 here. So we can use tabular multiplication, mod x to the 4th. Notice we have a 1, 2, 1, 0. Now, why are we going all the way out to this line? That's because we're concerned with up to x cubed. And so since we're working x to the 4th, we label everything out to the cubed position, because everything beyond that is swallowed. So we're going all the way out to right before the swallowing. And notice that we actually get things that this column actually becomes important. So that's why we just kind of put a 0 placeholder there. So we have a 1, 2, 1, 0, all right, to represent that polynomial. And then going down, we have a 1, 2, 1, 0 going down, and times itself. And we we just take this, we shift it over one each time, then we just kind of list these numbers out, multiply, add, we get this guy. So that's what that is, and we're raising. So we have, and that's when we took this and squared it. So basically we just have this polynomial, which is this one, and we just have to square it. So we do tabular multiplication again. This way and that way, shifting and then multiplying and then adding. We're only concerned with this column. And we get a 56. That means there's 56 different binary bits, different ways of getting those 3 ones, which means there's 56 different binary bit strings where you have 3 ones and your length is 8. So let's cast another perspective on this. Instead of just using x's, let's use a y, and let's have y have a meaning. That one digit is 0. Okay. Instead of being x to the 0, let's let it be y. Let's let it be y to the first, which makes sense because when you multiply y to x, it doesn't add anything to the exponent of x. So it's as if you have an x to the 0, and that's just fine. But it kind of gives you a little bit of perspective here because when you what we have is we're multiplying. If we think about the committees this way and we have x plus 8, y to the 8th, what's happening is we're pairing, we can either pull an x or a y from each thing, right? So if we want 3 x's, meaning 3 ones, then we're going to have to, the other 5 we would have had to pull a y from. So the term we'll be looking at to find the coefficient of is x cubed y to the 5th. So it's kind of telling, I guess, because this says there's going to be 5 zeros and then 3 ones. It'll work because the 5 doesn't interact with the 3 at all. And so we should also, the coefficient of this should be the same. This should also be 56. You can also think of it this way. You're multiplying out x plus y, 8 times. And when you're multiplying it out, you can you either pull an x or a y from each factor. So that's like saying at each factor, you're either pulling an x or a y. It's kind of like saying the factor itself is an object. And you're either throwing that object into a bucket labeled with an x or a bucket labeled with a y. So since you have 8 factors, it's like saying you have 8 objects and you're trying to figure out how many different ways there are of putting 3 of those objects into the x bucket and 5 of them into the y bucket. But see, if we put 3 of them into the x bucket, that actually means, and we say that's all we're doing, since we're throwing them all into one or the other bucket, that means that definitely 5 have gone in. So really it's the same question. How many ways are there of taking 8 things and putting them and collecting just 3 of them? That actually is the same question. So it's like 8 things and you're choosing 3 of them. How many different ways there of choosing 3 things from 8 things is really another way of looking at the situation. Okay, so let's think about a nice way of calculating this, of that coefficient, using derivatives instead of polynomial multiplication. So let's consider x plus y to the 8th. And let's for a minute pretend that y is a constant and x is the variable. So we're going to take derivatives with respect to x. All right. So what we're interested in knowing is the coefficient of x cubed. Now that coefficient will have a y in it because we're going to assume that the y is constant here, and that's fine. So we might see that in the end, but let's just kind of see what happens. So in the end, we're looking for, when we multiply all of this out, x plus y to the 8th, we're going to have a term that has an x cubed in it times coefficient a, and that a will have y's in it. In fact, it'll have a y to the 5th in it. But let's just kind of think about what happens when we look at just that one term in the multiplication. We multiply all this out, and we'll see what happens to that one term when we take derivatives of the resulting product when we multiply it all out. So when we multiply it all out, we get a big long thing, and we're going to be taking some derivatives. But let's just concentrate on what happens to that particular term as we take derivatives. Let's take derivatives until we just get a constant with respect to x. So there's no x's. It's just going to be something even with y's in it. So when we take three derivatives, see, so since this is x cubed, we have it times 3 times 2 times 1. So we get 3 times 2 times 1 times a. A is what we want to find, right? We want to know what that coefficient is. We're hoping that that coefficient is 56y to the fifth. 56, and then we need a y to the fifth in there as well. So that's what we're hoping a to be. But let's see how, if we could actually find that in the computation here. So we know that when we take the resulting product and we take three derivatives of it, if we just concentrate on the x cubed term, which has the coefficient of a, we'll end up getting this. So in other words, after three derivatives, this term actually becomes the constant term. That's actually very useful, because when you plug in like x equals 0 or something else into a polynomial, you always get the constant term out. So that might actually turn out to be pretty handy here as we go along, to have a constant term. Let's look at this another way. Let's just think about not having it all multiplied out, but before, when it's just like this, let's take a derivative. So when it's just x plus y to the eighth, we can use the chain rule. Take one derivative, another one. See how we're getting this 8 times 7 times 6. Okay, so the derivative of this is actually equal to this. And but we also know that its constant term is this. So after three derivatives, we have this with a constant term of this. To find a constant, you just plug in 0 for x. Let's see how that works. Plug in 0 for x. Oh my goodness, we get that times y to the fifth is equal to, so you just divide. Oh my goodness, this is what you get. You get 8 times 7 times 6 over 3 times 2 times 1, which we'll label as 1 times 2 times 3 and 8, 6, 7, 6 in this way. This is what you'd call a binomial coefficient, meaning 8 choose 3. We computed it. So how do we write this out computationally? So 8 choose 3, that means we're choosing three things to go into the X box, for instance, or the X bucket. So notice how we have three numbers on the top and three on the bottom. On the top, we start at 8, go down, 8 times 7 times 6. On the bottom, we start at 1, which is the bottom, and go up to 3, where you have three things multiplying on the bottom, three things multiplying on the top. And there's some notation for this, like if n were 8 and j were 3. But you can also say it's the same thing as choosing 5 things, right? 5 things to go into the y bucket means there's 3 things that went into the x bucket. So really, these two coefficients would be the same. Sometimes you can actually use this notation as well, n, j, k, if you wanted to. From n things, choose k things. And the way to compute this is, so if you're choosing k things, for instance, you have k things on the bottom, k things on the top. On the bottom, you start at 1 and go up. On the top, you start at n and go down, and you just make sure you have k factors on the top and k factors on the bottom. Or for j, similarly. Now, you can actually use factorial symbols to get this. Notice that if we have n and we're multiplying it down to a particular position like j plus 1, then if we multiply j factorial on, right? So if we multiply j factorial on, the j factorial would cancel, let's say j factorial on, and on the bottom, if we had j factorial times, okay, I guess, yeah, maybe that's not the way of saying it, but right. But if we have n multiplied out from n all the way down to 1, right? And I guess if we just stopped, right, if we had k going down the rest of the way, right? And we can kind of think about k factorial as being a factor of n factorial. If we cancel that out from here to here, how many things do we have left on the top that we're multiplying? Well, if j plus k is actually equal to n, which it will be, let's like 3 plus 5 is equal to n, then actually if we cancel out k on the top, we actually have j things on the top. So j things on the top, j things on the bottom. Or we could have done it with j, right? So if the last j things, we cancel that out, then there's k things left. So k things up here over k things down here. So it kind of works out. You can also use factorial notation to describe your binomial coefficient, which is read and choose K. All right, so 8 choose 3 is a binomial coefficient. You can throw this into a calculator computation system. It'll output the result of this binomial coefficient. Let's look at another example here. Example 3. Suppose that we want to figure out how many different ways there are of moving from the origin in 3 space to a point 2, 3, 5. So we're using coordinates x, y, and z. And let's just kind of look and see what that might look like for a second. Okay, so if we have a coordinate system, okay, or think of the xy plane, right? But let's kind of put the xy plane so it's lying kind of flat. So the x-axis, y-axis is kind of negative y, negative x, and you kind of think of it as sitting in a piece of paper that we've kind of put out this way. And then let's think about putting a new axis that goes up above the paper, call it the z-axis. So we have x-axis, y-axis, and a z-axis going up. So we're starting at the point 0, 0, 0. So that means an x coordinate of 0, y coordinate of 0, 0, and z coordinate of 0. And we want to move to a particular point, 2, 3, 5. So this means we go 2 in the x direction, we go 3 in the y direction, and we go 5 up. So we go up there, we kind of make a box over, and it's up in space. It's going to be up in space above the paper up here. So it's kind of like going to the point 2, 3 in the xy plane, then going up 5. So it's kind of a point up there. The question is, how many different ways are there moving from this point to that point? Okay, we are only allowed to move 1 unit at a time in only the positive x direction or the positive y direction or the positive z direction. So we can only move like parallel to the x-axis or parallel to the z-axis positively, or parallel to the y-axis positively, and 1 unit at a time. How many different ways there of getting from the origin to that point? Well, we can use binomial coefficients or multinomial coefficients, actually, to the rescue. We'll talk about what that means and what that is. So via this example, we'll get there. All right, so let's kind of think about what's going on. Let's see, these restrictions tell us we have no choice but to move 2 units in the positive x direction. Aha, so we have to have 2 moves that go that way, right? We have to have 3 moves that move in the positive y direction. We have to have 5 moves that move in the positive z direction. I guess the only question then is, which order do they go in? So do we do these ones, like one of these, then one of those, then one of those, or intermix them? Like, how many different ways are there intermixing all these things up to get from one point to another? At least we know we have to make 2 moves that way, 3 moves that way, and 5 moves that way, right? Okay, so the number of ways to each, okay, same. So we can think about them. Okay, it looks like the number of ways of destination is the same as the number of ways of taking 10 moves. Take the moves. And we're taking 10 different moves and we're putting them into different boxes. That's kind of like having a string, right, of length 10, and each one you can have different things happening and you want something to happen. But the point is we have 3 different things going on, so it can't be a binary string. So this interpretation is actually a nice one to use. You have 10 different moves and you want to say, okay, each move will go to a box. Either we'll throw it into the X bucket or the Y bucket or the Z bucket, but there's a total number of things that can go in each bucket. So let's think about committees. What is each committee is going to be? So each committee is a move, all right? So we can think about each committee as being a move. So we're going to pull something from each committee. We can either say pull an X, Y, or Z. Notice we have 3 different variables representing the 3 different buckets, right? Because we can either throw this factor or this committee or whatever think of this whole committee as a factor or as an object, and you can either throw it in there, right? And each object only has one, is only one object, so it can only go in one place, right? So there's only one way of putting it in each thing, if you think of it that way. So our committee is just x plus y plus z, and that's the same for every other committee, for what we can do for each move, right? So each move can be represented by x plus y plus z. We multiply all of those together, and the goal is to find the coefficient of x squared times y cubed times z to the fifth. Okay, so two in that bucket, 3 in that bucket, 5 in that bucket. Whew, okay, how do we do that? We just need to find the coefficient. So if we multiply all that out, we find that coefficient. All right, so let's think about how we might do this. Well, let's simplify this. You see how we have x plus y plus z? Why don't we just do a substitution? Let x plus y be u. So we get u plus z to the 10th. Then we can actually use binomial coefficient magic to figure out what we want. Okay, so in particular, what we're after is z to the so we're after the z to the fifth term, right? We're after the z to the fifth term. So why don't we look at the u to the fifth, z to the fifth term? Why did we pick u to the fifth? Well, that's because 5 plus 5 is 10. We're raising this to the 10th power. At least this will have a z to the fifth in it, right? And so the only option is we have to have a u to the fifth going on here. So we know the coefficient of this right here from the definition of what binomial coefficients are and what they do. They give us coefficients when we have something like this. So if we want to know this guy, since we're choosing like 5 u's, we'd have 10 choose 5, or we could do this one, but it's also 5, 10 choose 5. So this right here is how we would compute this. So 10 choose 5, the computation in here with 5 things at the top, 5 things at the bottom, whatever, that would be this number. So we're well on our way. So we get this number, but then we can replace what u is, x plus y to the fifth, z to the fifth. Okay, now let's kind of look at what's going on in here. What are we interested in getting out of x plus y to the fifth? We want an x squared y cubed. Well, we can find that coefficient in there with raise it to the fifth. It's 5 choose 2 or 5 choose 3. They're the same thing, but it's simpler to pick 5 choose 2 in this case. So we have, actually the coefficient that we're after, or the term that we're after in here is the x squared y cubed term, which has that coefficient. And when we multiply this out, like everything else we could distribute the z to the fifth to, would give us something different. So we really don't need that. So in the multiplication, really all we need is this. This is a whole lot of stuff, but there's one term in it we're interested in. So just distributing this in and that into that one term will give us the result. So doing that will give us this, 10 to the fifth, 10 choose 5 times 5 choose 2, and we get that. Now, if we work out the computation here in terms of factorials, 10 factorial 5, 5 factorial, 2 factorial, 3 factorial, we notice something interesting. We get 10 factorial over 2 factorial, 3 factorial, 5 factorial, 2, 3, 5. Oh my goodness. This is a nice computation for something called a multinomial coefficient. If we're looking for the coefficient of x squared, y cubed, z to the fifth, and we're raising it x plus y plus z to the 10th power, we just simply take 10 factorial divided by 2 factorial times 3 factorial times 5 factorial. And we get this. This is called a multinomial coefficient. So total moves over number of x moves, factorial, times number of y moves, factorial, times number of z moves, factorial. This is a multinomial coefficient. And we will end this this read along here, right here at this particular example. Thanks so much for watching.